Good morning, good afternoon, or good night, depending from where you are listening to me. My name is João Pedro Braga, and I am a retired professor from Federal University of Minas Gerais, Brazil. Before I start the lecture, I would like to give you some prerequisite about the lecture I'm going to give. And I'm going to this desirable knowledge talking about my books. I have one book on physical chemistry. It's a one semester course. Basic quantum chemistry, another book. It's a 2 semester course. I have the second edition of this book, which is going to be very important for the lecture. It's about statistical thermodynamics of atoms and molecules. I have another book on numerical methods in quantum chemistry, and a book in history of chemistry that was about the visit of Marie Curie to Brazil. This book was translated into Polish. Therefore, for the lecture today, it's desirable that you have a knowledge of basic physical chemistry, basic quantum chemistry, and the basic statistical thermodynamics. Actually, only physical chemistry and statistical thermodynamics, not so much quantum chemistry for the lecture today. The lecture today will be about the Carnahan-Starling equation. We have studied before the second virial coefficient that was good to describe gas phase. But if you increase the density of the system, more terms in the virial expansion have to be considered. In this chapter, in this lecture, I will make the calculation for the third virial coefficient and justifying the terms in the Carnahan-Starling expansion. Therefore, this chapter is about the virial expansion under the hard sphere system. Before starting the discussion further, I'd like to remind ourselves what we have studied on chapter 17 of my book on statistical thermodynamics. There we assume that the total potential could be described by a summation of pair potentials, which is of course an approximation. In this case, consequently, the Boltzmann factor is going to be a product. The Boltzmann factor for the total potential is going to be a product of the Boltzmann factor for the pair potential for individual pairs of potential energy function. If you introduce the Mayer function, you arrive at this expression, which is exact under pair potential summation, and this expression can be developed as that if you put several terms. The first term will give rise to ideal equation of state for an ideal system. The second term, this term, will give rise to the second virial coefficient, and this one for the third virial coefficient. The reason is the same, so I'm going to do it only for the second virial coefficient, but if you want to do the third, of course it's much more laborious, but it can be done in the same way. So if you calculate the partition function, develop the Mayer function for the pair, group the terms, It's very well explained here. And if you calculate the partition function and so on, the algebra is done there in my book, you arrive at the virial expansion to second order on density. If you consider this term, you are going to get the third virial coefficient with the density, including the density up to the third order. After the last discussion, I will just summarize the main points here because they are independent books. So this we have seen in the previous discussion. Meyer function as well. That's the book chapter 17 of the book. That's the virial expansion up to the third term. You see, it's square, but it's actually third in the density because there is 1 over density here. So if you move this 1 over density to the other side, it will be density is square, density to the cube. And the expression you get for the second virial coefficient, as before, as in the last discussion, is equal to that. And as I said, it is laborious, but it's possible to get this expression for the third virial coefficient. We are now in a position to calculate the third virial coefficient, as I said, using the hard sphere approximation. Just remember something about the main physics of hard sphere. Actually, I give it as a problem. That's the potential of a hard sphere system. The diameter here is 1. That's the Boltzmann factor, start at 0, and then it's 1. And that's the Meyer function, start at -1, and then is 0. I'm going to use this Meyer function to make the calculation. These two functions are basically the same, you have just to subtract 1, and they will be important later when we are going to study at a point where we are going to study correlation functions. Therefore, that's the function for Meyer function. It's -1 if r is less than diameter, and 0 afterwards. Just an example, let's calculate the second virial coefficient using this function. See, you get the same result we have obtained before. To calculate the third virial coefficient, we are going to use the Fourier transform, the direct Fourier transform, and the inverse Fourier transform. The definition of direct and the inverse are the same, just a question of point of view, because the integral is the same, you see? Integral is the same for a central field potential. That is, for a function that depends only on the scalar of the function. This integral, you have to make this spherical transformation. You have to go to this spherical coordinate, and also I give it as a problem how to establish this integral. With that in mind, I can put the Meyer function again here, and I can calculate gamma, which will be important to calculate the third virial coefficient. This integral is simple, we just make it by substitution. Now, from this definition, you see that I can get the function of ρ3 minus ρ2 that I will need here. From this definition, I get this, and I substitute it on this here, on this expression here, right? And then it goes to here. That's the expression for the third virial coefficient. but I have substituted that. Then I split the exponential, and it is very easy to see that's 3 gamma functions. So this integral of the third virial coefficient can be expressed as the cube of this integral that we have already done. That's the next step. You see, I put here the gamma function to the cube, develop, and I will end up with the problem to solve this integral. It is a laborious integral. It has several steps, but it's not difficult. It can be done with the elementary calculus. Just make substitution. Or you can expand the cube and use the complex form of the integrals. The important point here is that you get this result. With this result, we plug it again here, make the expansion, simplify, and we are going to end up with the third virial coefficient, which is 5/8 of the second virial coefficient squared. We now have the third virial coefficient and the second virial coefficient. And you can have a better approximation for the compressibility factor. I substitute the second virial coefficient here and the third here, and make the expansion. VE is the volume of each sphere, and rearrange terms, define a new quantity, eta, which is the volume of all these spheres and volume of each sphere, or that is the volume of all these spheres over the volume of the container. That's the definition of eta. If you simplify, you get the density pi/6 times diameter to the cube. Using this new variable in the compressibility factor expansion, after rearranging the terms, I obtain that 1 4 eta plus 10 eta squared. We are now ready to start to understand the basic principle of the Carnahan-Starling equation. Ree and Rover, they made a hard sphere simulation, propagating equation of motion, and from these results, from the pressure they got, they obtained the compressibility factor in this form: 1 4 10, and of course you can see it here. These three terms are already the terms that we have obtained theoretically, and this is by classical simulation, but they had more terms: 18, 28, 39, and so on. Carnahan and Starling, in a very clever way, they approximate these numbers by 18, 28, 40, 18, 28, 40, and they realized they could see that is actually a series of these terms. In this way, they have included all the virial coefficients. And this series converges, as I showed in the problem, this series converges to this term. That's a very precise compressibility factor, and it's called the Carnahan-Starling compressibility factor. This coefficient, 18, can also be understandable if you take into account the fourth virial coefficient. The fourth virial coefficient is given by that. It was first calculated by Van Laar, and then it was also calculated by Boltzmann in 1899. He obtained this result. And if you put some numbers here, you obtain this value. The fourth real coefficient is 0.28695 times second virial coefficient to the cube. If you run this code, you get this result. But you see, you can justify now the 18 factor in the re-and rover calculation. Look at that. B4 over b squared to the cube is equal to this number, but b2 is 4 eta, as you have obtained before. So the factor will be this number times 4 to the cube. Since it's a cube, I got 18.37, which is the same number. Re-and rover, probably this is more precise than the classical calculation. The Carnahan-Starling complexity factor can be compared with the re-and rover results. But as I said, Carnahan-Starling is much more precise. The re-and rover calculation go up to the 5th power. And for Carnahan-Starling, there is infinity, the series goes to infinity. So, if you want to reproduce this graph, just have to run this result. Not this result, this code. The last section of this chapter is the section of problems. The first one we have already discussed. It's about hard sphere. The second one is the integral that appears on Fourier transform. Got this form. It's very easy to carry on this integral. Just transform to spherical coordinates, make this substitution, integrate. You got this result that we have used before. The third problem is how to obtain the Carnahan-Starling equation. Also, you just have to make this substitution and check the equivalent that this series is equivalent by making this substitution into that, and then use two series, this series, and you multiply this series by the numerator, you get the Carnahan-Starling equation. Right? The fourth problem is, I ask you, I have already discussed it as well, the fourth and the fifth. So that is the chapter on the Carnahan-Starling equation that I would like to show to you. Thank you very much.